Hi guys, and welcome to Thursday session of week 5. We have quite a few interesting things that are happening. I mean, starting actually from today in terms of the exam review. So you have an exam review that was posted to Canvas. So I'm hoping that you guys will take it as soon as possible. You will have a chance to, if you cannot do it today or tomorrow, to work on it over the weekend. So you have ample of time to start working on it. So I would suggest you start right away because it's a lot of materials to cover. And it's units basically that we started with unit 5 all the way to unit 35, which is finishing today. So those are part of the exam. So you make sure that you cover all of these topics. And since the review it's not timed, so you can take it as much as you can, and it's useful review to help you prepare for the actual midterm. Now, the review itself is graded, so you have to know that. I mean, you're going to receive a grade for doing the review, and you're going to receive a full mark regardless of what you do in the review. So if you score, let's say, for example, 50% in the review, you are still going to get 100% for it, just basically to make sure that you guys are engaged with the class, that you're actually doing the what you're supposed to be doing to prepare for the exam. The grade, though, is going towards your participation. So it helps you basically make sure that you're fully engaged with the class, as I was saying. Now, the actual exam is actually on Thursday next week, okay? A week from today, that is. I mean, today is what, the 15th? On the 22nd is actually when the exam is. It's going to open from 8 o'clock in the morning until like 11 p.m. You have ample of time to take it. It's a timed exam. It's only basically one attempt at it. So once you take it, you cannot stop in the middle to decide to go into something else and come back. In other words, before starting the actual exam, I'm not talking about the review. I'm talking about the actual midterm. So when you start the midterm, make sure that you have all the time it takes to finish the midterm. And then after that, you can do whatever you need to do, which means a week from today on the 22nd, we will not have a live session. That day is dedicated just for the exam. So basically, there will be no live session like the one we have because I will be on the computer trying to respond to you guys. Granted, between 11 and 2 o'clock, I am teaching another class, so I will not be available during those times, but I'm available before 11 o'clock in the morning, and I'm actually available at 2 o'clock, which is our meet time, to answer any of the problems. Then at 5:35, I also will not be available because I have another class that ends at 9 p.m. Meaning, all of you must start the exam before 5 o'clock. Really, if you expect any kind of, if you think that you might have any problems or something like that. Any person coming to me and sending me a message saying, hey, there is something wrong with the exam, or the exam is not opening up for me, or something is not wrong, or closed on me, or whatever, some reason. And if it's something that is, we can work it out, we can, especially if there is an issue with the actual exam itself, like for example, a question is you think is not showing correctly or something like that, or it's showing something that is not supposed to do, then in that situation, I can intervene. Granted, it's done before 5:30 p.m. because after that, as I was saying, I have another class, and that class actually ends at 8:35 p.m. By 8:35 p.m., it's too late to do anything, even because most of you guys would have been done by then, and it's too late. Basically, we have to live with whatever problems we have at that point because you need to start the exam by then, okay, and then finish it before 11 p.m. Does this make sense to you guys? Okay, very good. So obviously, the more you get into it, and I know some of you who are sitting in the lab, so they know exactly what I'm talking about. At 5:35 p.m., we actually have a lab, so we cannot really do we cannot really intervene at that point online. So again, you will be receiving further basically instructions via Canvas. And if you start the review, you will see exactly what I was talking about in terms of the review and how it's graded. It's a graded assignment, and its grade goes towards your participation. There are only two grades are acceptable for the review, either nothing at all, that is if you don't do anything, if you don't do the review at all, or full credit. Basically, there is no in between. You're not going to get 50% or 75% or 23% or whatever you can think of, anywhere between 0 and 100%. Only 0 or 100%. So that's the only way to get 0% is by not doing anything. Even if you start the review and you answer one question, and that question happened to be wrong, so Canvas will give you 0% in this case, okay? I will come back later on and override it and give you full credit. I assume then that you're going to complete the entire review and you're going to give it its due diligence, in the sense that you're going to give it the time to review all the questions and all the materials related to it and finish it. So that is basically from me to you guys to help you prepare for the actual midterm. Okay, so okay, very good. So let me get into, because we still have a big unit, which is unit 35. And I was debating whether or not we should start a new unit, namely unit 37 at this point. So we will see how it goes with unit 35, and most likely probably we'll just introduce that unit. So it's going to be a short session today because of that. And the focus again is actually for you guys to start doing the actual review, okay? Why it's not letting me open these things in here? Trying to open. Okay, so I have to have OneDrive open first before I open a file from that OneDrive. And then go here, this folder, this folder, this one, Astronomy, and then unit 34, 35, 7. Okay, good, it's opening. So let me go back into Canvas, into Zoom, and let me share with you, share this one. So unit 35, oops, that's not what I want. Unit 35 deals with the basically how the solar system formed, okay? And how did we come to know that? How did we basically decide that, or at least come to the conclusion that the solar system formed this way and not in another way? So obviously that is a key question to this. I mean, anybody can tell you any story, but you have to always ask for the evidence. And the evidence in here is based on radioactive materials. They have a property, every material, called the half-life. That's basically, the idea is the following. If I take a sample of a material, uranium, doesn't matter, as long as it's radioactive, okay? And let's say, for example, I take 1 kilogram of that material, just to make it easy, okay? I ask the following question. How long from now until half of that uranium is gone? And I will be only left with half. In other words, 500 grams are left from the 1 kilogram I started with for uranium. That is, by definition, the half-life. Radioactivity is a statistical event, meaning it's a probabilistic event, meaning that if I have a single atom of uranium, it can decay, it can change from uranium to another form with a probability that is basically can be now, it can be 5 seconds later, it can be an hour later, it can be 3 days, it can be a month from now, it can be 1,000 years, 100 years, 100,000 years, and so on and so forth. So a single atom itself, you cannot really make a precise prediction when it's going to decay. That's one thing. But if you take bunch of them, like for example, in the case of a 1 kilogram, you have a huge number of these atoms. You have a number that is of the order of the so-called Avogadro's number, which is of the order of 10 to the power 23 kilogram, 23 atoms. So now it becomes more precise. With more basically atoms, then it becomes more precise. Then we know exactly how long it will take for a sample to drop by a factor of half. We call that one half-life. And this is a characteristic of the material. Every material has its own half-life. And this is a constant everywhere. Okay, this is a useful piece of information because if I know, for example, that a given element cannot be formed except through radioactive materials, and if I have a rock, for example, a meteorite that I can take, for example, and I put in the lab and analyze how much do I have from the original element and how much I have from the subsequent element that formed from that when it decays. So that is the idea behind it. Once I find that ratio, since I know the half-life of that material, I can tell you how long ago did this material basically form? How long ago when I had the entire thing, only the original material? There are some words in here that are used in radioactivity, sort of terminology. The original material is called the parent, and all of the subsequent, basically children, if you wish, are called daughters. So that is the terminology that is used. So the daughter, how many daughters I have versus how the original parents, and the ratio of the two is what gives me the precise life of this, how long ago this basically rock I have, or this meteorite I have is old. And the emphasis on meteorites is because unlike rocks on Earth, they get basically, they're involved in the geology of the Earth itself. So they could be basically a how should I say, they are not pure. They are not really the original stuff from when the solar system formed. Meteorites, on the other hand, those are coming from ancient rocks that formed when the solar system formed. So those they provide us with an accurate, precise, basically more precise, I should say, more accurate determination of the age of the solar system. So that is basically how we came to know all of these things. Obviously, there are some details of also how the solar system formed from the motion of the planets. They all tend to be, first of all, on the same plane, and they all tend to be moving in the same direction, and they all tend to have more or less the same tilt. I mean, they're more or less pointing in the same direction in their rotation, their own rotation, internal rotation, versus their rotation around the sun. So that is also more or less in the same direction. There are some exceptions, though. Those exceptions are, for right now, need to be forgotten, and we will come back later on to explain each and every one of these oddities. But in general, as a general theme, there is only one pattern. So that led us to the solar nebula theory to explain how the solar system came out to be. Basically, like you take a dough and you work it out, and as you spin it further and further, it flattens, and all the pieces will be moving in the same direction. So that's in a similar fashion. Now, what determines the whole process is actually the force of gravity. The force of gravity is the one that pulls all the material together, because the force of gravity is the one that pulls different pieces closer to one another. And as it gets bigger, the force of gravity intensifies. So the process accelerates over time. So initially it starts slow, because the masses are small, and when they are small, they attract with each other, and the distances are far too. So both combination of these two, so the attraction is kind of small. But once the first pieces start to form, the next ones are actually easier to put together, because now you have a central location that has more mass, and it can attract toward the smaller masses and accumulate. The more it accumulates, though, the faster the process is, because the more the force is and the more it's going to build up, basically. So during this process, the sun formed first. But the sun, as it started to, the material started to come together, they lost that potential energy, because if I, again, and I know I did the example last time, if I take this object, for example, and drop it, it's going to fall. Why? Because it has potential energy. And when it does fall, it's going to lose that potential energy. But energy is conserved. Where is the energy going to go? It's going to convert to potential energy. Okay. I'm sorry, to kinetic energy in this situation. So it was potential. Now it's kinetic, energy of motion. From the study of thermodynamics, the study of heat, basically, when molecules, when parts start to move faster and faster, the temperature increases. So the process of coming together increases the temperature of the central part where the whole thing is gathering, because that's basically the process through which as the material coming closer, they spin, and as they come closer, they spin faster and faster, and in doing so, the temperature inside increases further and further. In a sense, that's how basically the sun formed, and it was really the biggest thing inside the solar system that was forming. There were some disturbances in the gases that started to come together, and those disturbances created other basically chunks of matter that starts to form also. That was actually how the planets formed. So while the sun was still forming, Jupiter starts to form first. How do we know Jupiter starts to form first? Because it's the bigger one of them. Had it been Earth that starts to form first, then Earth will be bigger than Jupiter because it will have more time to accumulate matter. But no, it's Jupiter that starts to form immediately after the sun basically starts forming. So, and Jupiter, because it formed early, starts to gather more and more materials. Then after that, of course, comes Saturn and the other two gas giants, and then the inner planets. So that's how the process starts. But because the sun started first and it was in the center, the reason why it was in the center is because, again, the materials were coming to the center. They were not going anywhere else. And it started to gather more and more materials. Its temperature starts to go higher and higher at the same time, just as much as Jupiter and everybody else also that's basically forming. And as the temperature of the sun gets hotter and hotter and hotter and hotter, and more materials gathering and gathering due to the force of gravity, at some point, well, first of all, let's talk about the initial composition of the solar system and the solar nebula that basically made the sun. It's mainly hydrogen for all practical purposes. 75% of it is hydrogen. And the other 25% of it is helium, with traces of other elements. Those elements, the main one is actually lithium, and then some other elements, including iron and nickel and all of the rest of the elements in the periodic table. So that is basically how the sun, since it was really the biggest player, it's mainly hydrogen. The outer layers, they're further away. They're still coming down, and the inner layers, they already came down. So the inner layers are moving faster and faster, and the temperature inside was hotter than the outside. The temperature reached millions of degrees. Once it was 15 million degrees, and the pressure was high enough, and the hydrogen that forms inside inside the core of the sun, at that point, it was too close because of the tremendous pressure exerted by the force of gravity, basically the incoming of the materials. At that point, the sun became nuclear, started to fusing hydrogen. The minute it did that, it moved from a protostar stage to an actual star. It became a star. So that explosion basically pushed the materials that are still coming inward. So that nuclear reaction, and instead of further materials going down, at that point, a balance was struck between the falling material, which is mainly hydrogen and helium, towards the center due to the force of gravity, and the outward pressure coming from the nuclear reaction that produced more heat. So at that point, the sun stabilized. And that is really the onset of the solar system, because once the sun became a star, that is the start of the solar system. Other planets continued to form, but when the sun basically went nuclear, the radiation that came from the initial blast basically scattered a lot of the materials that were forming the planets and the moons and the different stuff that was in the solar system. So in a sense, what the sun did was it starved the remaining of the planets from further in growing. And the biggest player, of course, is Jupiter. Jupiter was in the same process as the sun, was still gathering material, getting hotter and hotter, but its internal temperature did not reach the high enough temperature to also become a star. Had the sun delayed its operation to become a star, Jupiter would have continued to grow and would have become a star too. And had Jupiter also and the sun did not go nuclear and basically become stars, most likely also the same scenario could have happened for Saturn and so on and so forth. But here, there is an imbalance between the sun and Jupiter. In a sense, the sun is much, much bigger than Jupiter. So there is no way this process could have continued that way. The sun went nuclear. That initial basically explosion expelled a lot of the materials that were in the solar system and sent a lot of stuff every which way. Some of it were captured by the planets. Some of it escaped the solar system. Some of it fell back on the sun. And in doing so, basically the planets start from basically further gathering more materials. So the sizes basically were determined at that point. Obviously, there were more stuff going on in the solar system, other planets moving around and colliding with one another, or colliding with the moons next to them, and the materials that were left in there, at least the big enough materials that were not blasted away. Those later on, they fell back on the planets, and they fell back with a lot of intensity, and that is the so-called early bombardment stage. So this is in a nutshell how the solar system happened. There are a lot of reasons why we believe this is correct. First of all, evidence through it, the motion of the planets, the sizes, all the models indicate that this is what happened to the solar system. In addition to radioactive radiometry, which is the dating basically using radioactive materials, and also the shape, or at least the face of the moon, for example, if you look at it, or Jupiter, or Callisto, for example, near Jupiter, those moons or planets, for the case of Mercury, that did not have an atmosphere, they have the evidence for that early bombardment. If you go outside and look at the moon, you will see that it has a lot of craters in it. Okay, those impact craters, they are actually an indication of what happened earlier in the solar system. So in other words, there's a lot of evidence for this one. It's not just something that is kind of a story without any evidence. So that's basically the evidence for it. And the last point in here is differentiation. And this happened for all of them. Well, when the material come together, it was hot, okay? For example, when the Earth was initially formed, remember that heat where everything came in, it was hot, okay? Well, the heat started to escape to the environment, to the surrounding. In other words, through radiation, the Earth starts radiating energy away. Now, that heat, I mean, the materials started to basically move around. The heavier elements or the denser elements, namely iron and nickel, starts to sift inward, and the lighter element starts to sift upward. In other words, that's how the Earth and actually all of the planets must have happened to them. The denser materials, they go inside, they fall, and the lighter materials, they rise. So this is what we call the process of differentiation. So that's what happened to the Earth, its core, and I believe that's also the same true for all of the other planets, is mainly those highly denser materials, especially iron and nickel. And then as you move up in the layers of the Earth, for example, or the other planets, at least the rocky planets, they're made out of silicate that's at high temperature, and then the mantle, and then those silicates starts to get cooler and cooler until you get to the surface, which is mainly this rocky structure, which is really silicate. I mean, silicon plus oxygen. That's what the silicates are. They're oxides of silicon. So that is mainly what those materials, plus traces of all of the other elements, lead and all of the other stuff that is part of the planet. So this is in a nutshell what the entire unit is. Okay, so I'm hoping that you guys go to the book, open it, go through the entire unit itself so that you understand what's going on. Okay, so let's quickly browse through this. So again, the age of the solar system is dependent using this formula really, okay? 1/2 the time that has lapsed divided by characteristic time, and that characteristic time is your half-life, okay? If the time that has lapsed is exactly half-life, is this formula needs to be probably, yeah, they use the symbol tau in here, okay? But in the literature in here, they have the letter T. It's the same thing. So basically the half-life in this case, it's tau, okay? The Greek letter tau, okay? And that is basically how, if in exactly one tau passed, meaning exactly 4.5 billion years for the case of potassium, okay? Then we're looking at half of the potassium will be gone, okay? No, I'm sorry. Potassium, I mean, the determination of all of this is 4.5 billion years. I'm sorry. What is the half-life of the potassium in here? You know what? It's not 4.5, but I can find it. $1.25 billion years. That's the answer to it. Okay, so where's the... So potassium half-life is 1.25 billion years. So if I come to this formula in here and put 1.5 billion, then it will tell me 1/1 is 1, so it's going to tell me half of it is gone. So let me stop sharing because it's kind of an interesting formula in here to work with. And let me see if I can find a calculator on my computer. It doesn't matter which calculator I have. Okay, any calculator would do, just to show you how these calculations work, because you might have some problems related to it. So hopefully, again, the point of doing calculations is really to help you understand. So let me go share the calculator itself. Okay. So what the formula says is 1/2 of the time that has elapsed over the half-life. I'm going to assume that the half-life is 1.25 billion years, okay? We're doing potassium. So, and we start, let's say, for example, with 1,000 grams, which is 1 kilogram. So we have 1,000 kilograms times open parentheses, okay? And in open parentheses, I have 1/2. As you can clearly see in the top in here, it's 1/2 to the power of, where is the power? So here is the power, okay? And it shows that basically like upside down V. So 1.25 billion, I'm gonna write just 1.25, assuming that the units in billion years divided by 1.25. I know it's 1, but just to show you how the math would work. So the ratio of 1.25 billion years over 1.25 billion years is 1. But what I'm doing in here, I'm taking 1,000 kilograms and multiplying it by 1/2 to that power. So the answer should be 500 grams. Okay, so 500 grams after exactly 1 full half-life, which is 1.25 billion years. Let's do the same math in here to see what happened after 2.5 billion years. So after 2.5 billion years, so I have still 1,000 grams times open parentheses 1/2 again, 1/2, 1/2 that is, to the power, and I'm going to open parentheses again. Now I decided it's twice as much time has lapsed. 2.5 billion years has lapsed, divided by 1.25 billion years. That is the half-life, always divided by 1.25 billion years. So in other words, we won twice. Now I should really have 250 grams left of potassium. Okay, so if I take a sample and I look for the argon and the other signature of the two daughters, basically for this case, which are the argon and calcium, and they add up to 750 grams. and the potassium that is left, potassium 40 that is left in this case is only 250 grams. So you could say, wait a minute, this sample is as old as 2.5 billion years. That's the age of it. That's how we do it. So now, if 3 half-lives, of course, you can guess it's going to be 125. So let's make sure it is 125. So we have 1,000 again, and this 1,000 is times 1/2 to the power of 3 half-lives. 3 half-lives is what? 3.75. 3.75 billion years over, of course, 1.25. Obviously, this should be 3 because I took 3. Actually, I'm multiplying by 1.25. That's why it has to be 3. So now the answer should be 125 grams left from the potassium. Again, if I take potassium, a sample that has potassium from the radioactive 40, and then they have the calcium that is derivative from this one, and also the argon that is derivative from this one. And if I take the argon and the calcium and see how much I have, let's say, for example, 875 grams. Of course, it could be as long as it's in these ratios, okay? And then 125 grams of it is just potassium. Then I can say with certainty that this sample is 3.75 billion years old. Okay, that's how we came up with it. So that's how we determine the age of the solar system, by doing similar studies. And the age of the solar system is 4.5 billion years old. So it's not 6,000 years ago. So that is not true. Okay. So whoever tells you that, basically you have to confront them with this ones in here. Okay. So that is. So the Earth samples are a little bit tinted. So at the end, we needed the rocks that are not changed, and that is really what led to this conclusion that is 4.5 billion years old. That is the Earth. The Earth is also an indicative of what happened to the solar system, and the solar system is actually, Earth is probably slightly younger than the solar system, because the solar system, remember, from the age of the sun, and the Earth was continued to form. But the point being in here is this is the age of the solar system. Make sense? Okay, very good. So this is again the graph that we have. This is what I was doing earlier, except I'm doing it for specific times. 1.28 billion. So it's not 1.25, it's 1.28. That's fine. Okay. It's the same thing. 1.28 billion, 2.56 billion, 3.84 billion, and 5. So this is basically the two daughters in this case, which happen to be calcium and argon. They start with nothing and they start to increase. Obviously, the argon there is a less probability for it to form from such a decay, and the calcium is the more probable one. So, and those are the ratios. So if you start from 100,000, you will be left with 50,000 in here, and 45,000 for calcium and 5,000 for argon. So the argon is less, and the potassium is more, and the potassium is increasing with time along with the argon, but in the same time at the expense of the potassium in this situation. So at any given point, I find the ratios and I can determine the age of the sample. That's how scientists actually were able to determine the age of the solar system. So again, when we looked at the solar system, we saw its shape, we saw the speeds, we saw also the different densities. The inner planets are more denser than the outer planets. So all of these things, as a matter of fact, when the sun blasted the materials, obviously the ones that are closer by it, namely the heavy materials and the lighter materials, that is, they get expelled from nearby of it, starving actually the inner planets from more gases. That's why the inner planets ended up being rocky. So that's the model fits beautifully with everything in here that we're talking about, and what we know about the solar system. Again, something happened in the region that we are in early on in the solar, before the solar system was. So there must have been giant planets, stars in here in this region that went through the supernova stage. And when they become a supernova, they produce heavier elements, because when we look at the evolution, when we look at the solar, the entire universe, we will see actually the best model predict that the universe actually, when it formed, it had traces of lithium or anything else, but mainly helium and hydrogen, with the ratio of 75 to 25. Well, in this region, we have other materials other than that. We have iron, we have nickel, we have potassium, we have gold, we have uranium, we have all kinds of other materials. And those, they cannot be formed by the early universe. They must have been formed, and they cannot be formed also with the small stars. Stars like the sun, at best, they can produce carbon. They cannot produce something that is more than that. But we have higher elements in the periodic table than this, so there must have been other stars in our region that must have been much, much bigger, not in our region, where the sun formed, because the sun moves around the galaxy. That basically led to the formation system. And not only that, some elements, they cannot be formed in the periodic table except between neutron stars. So not only one, but many, including some that form neutron stars, and those neutron stars collided. And in doing so, they produced the rest of the elements in the periodic table. So now you have that gas, intergalactic gas, basically, that is moving around, but it was in a dense region. And because of the force of gravity, it starts to come together. So that's basically what happened to the solar system. And as it does, of course, the inner ones is hotter, and the lighter one, the lighter material stays outside. And that's basically the analogy that is given in here. And this is basically how the temperature basically affects the condensation of this materials. And it's giving you in here their proportions on Earth. Okay, oxygen, silicon, and iron are the main components of the Earth. Okay, and but in the case of the sun, for example, it's mainly hydrogen and helium. I say 75% and 25%, that is the first generation, or at least the early stars that forms immediately from the original materials that formed the all the stars at the beginning. But the star is actually not the first or second generation. It's actually a later generation that formed from several of the stars that formed and basically one supernovae in its region. So the proportions of the hydrogen are less because more of it has been converted to helium after the universe formed. Okay. So again, this is based on spectroscopy, part of a lab that some of you sitting in Astronomy 125 will know, will sit in, and you will be looking at the spectrum and determine the existence first from lack thereof of certain materials in the given stars, including the sun, and their concentration. So it's really important, interesting stuff in here. Okay. So again, remember how that temperature, we call it the frost line. At this close from the sun, with this high temperatures, the iron starts to basically melt. Then, in this temperatures in here, it's actually, the closer it is, actually the silicate starts to melt, and then they start to cool and remain in their solid form. So this is why you have this rocky planets in this region. Okay. Then after that, actually water starts to condensate and become solid. Ammonia later on starts to condensate when pass through Saturn. So the moons there, for example, Titan, right on its surface, water is actually solid rock. And when Huygens actually landed on Titan, it has like rocky features, but the rocks, instead of made of silicate, they're actually made out of water. Okay. Methane is still actually in a liquid form at that point. There are lakes of it on the surface of Titan. As a matter of fact, Titan it's the only world that has oceans, or at least water bodies on its surface. And instead of water, they're actually methane in this case. Then past Neptune, we're talking about this when material starts to basically become, starts to solidify. So this is how the distance and the temperature impact the structure of the different planets. And because again, how the material starts to come together, okay? So again, the planetesimal is then when the material starts to come together and become basically smaller planets, if you wish. Those are the nucleus of the planets that starts to form, okay? And it's all due to the force of gravity and basically converting energy from potential energy to kinetic energy. It is a point that you guys need to be aware of. And that is because of the first line in here that it limits where the material starts to freeze, actually in terms of water and so those planetesimals past that line, they become made out of ice, in this case, water ice. Whereas the inner ones, they're actually made out of silicates, okay? Then came after they started, the material started to collide and they start to form this material up to the Kuiper belt. So again, the conservation of angular momentum ensures that everything stays on the same plane, okay? And as they do, that is basically the materials as they start to form. And depending on the region, if you have a lot of materials, for example, the outer planets, although the sun expelled a lot of the materials, they still had more materials together, and they continue to grow further than the inner planets, which remain small, okay? I already talked about the process of differentiation. Think about it. When you have materials, for example, and you start to let it rest, usually the heavier materials go down, the denser materials, they sink, and the lighter materials, they float. That's similar in a sense what happened to the Earth because it was initially hot. The materials, they were undifferentiated. Basically, they're still in every which way, and the density was more or less uniform. But because of the force of gravity, the denser material starts to fall into the core, and the lighter one starts to come to the surface, similar to what happened in a liquid, basically, okay? This is an indication of the age of the materials too, because if the materials are still young, then this is the situation which we should see. But this is basically where we are right now. As a matter of fact, you can follow the sun, the Earth 4.5 billion years ago based on its temperature and see how long it takes to differentiate to the form that we know it in here. So it's all consistent. So, and then you have this late state bombardment. And as I was saying, if you look at the moon, for example, or Mercury, or even Callisto, or even Ganymede for that matter, and some of the outer objects out there that don't have an atmosphere or they don't have a weathering. Like, for example, for the case of Venus, to have extremely thick atmosphere, and also it's hot enough to melt a lot of things. Earth also has that. We still have a lot of craters and impact craters on Earth and even in other objects. But for example, if you look at Jupiter, first of all, we don't have access to its surface, but the atmosphere in there will basically melt anything that falls on it. So again, this is part also of the history of the solar system. Immediately after it formed, there was a lot of debris, a lot of planetesimals floating every which way, and they're the leftover basically from when the solar system was forming. And that, because of the interaction of the solar system, starts to fall every which way. And those impacts were left, at least their prints, everywhere we can find them today. Some places we can't, but they were everywhere, uniformly everywhere. Some of them fell in the sun, some of them actually were well expelled completely from the sun, and a lot of them fell also on the planets and the moon and so on and so forth. And this is as evidence. And they have more or less the same distribution, the same age, the same things like that. So they're happen in the same stage when the solar system formed. Other craters formed later on, but they're scattered here and there. And how do we know they're happen later on? Because they're superimposed on the ones that are existing already. So if you see a crater and there is one inside of the other one, so this inner one, the smaller one, or the inner one must be later. So this is some of the methods of determining the age of also the objects just by counting their craters and seeing which one came later or something, and you can determine also the age. So this is another method actually of dating into the solar system, how you can find objects, how old they are in the solar system. Again, in terms of the atmospheres, of course, it happened in different fashions. When during volcanoes, for example, there is formation or actually expulsion of a lot of gases, and this is how the Earth actually got its atmosphere, and this is how some of the other planets also got their atmosphere, including Venus. Okay, some of them, like Mars, it's also got its atmosphere in similar fashion, but couldn't retain it. Okay. It couldn't retain it. That's basically what happened to it, because it's too small. Its gravity is low. Okay. The same thing is for Mercury, same thing for the moon, also, and all of the other objects. So they must have had some early volcanic activity, and but later on it was basically lost. And the water, for example, that formed on the Earth and a lot of the moons actually formed from the impact of comets that were coming from the region from the frost line, heavily loaded with this ice and liquid. And then when they impact, they basically vaporize and form those oceans, at least on the Earth. Again, the retention of the atmosphere depends on the object, how big it is. In the case of Earth, for example, and Jupiter, they are big enough to retain it. Jupiter actually had a lot later outgassing activity, namely forming more atmosphere, and that resulted in a super thick atmosphere. The Earth is actually having that process too. I mean, there are volcanoes on the Earth, and there are all kinds of activities to put gas in its atmosphere. Now, if it were not for this activity on the Earth would have lost its atmosphere also. It's replenishing it. It's basically all the time putting back more of the atmosphere. So that's what's going on. Except in the case of Venus, it put more than what it should really. But in the same time, it lost a lot of its lighter materials, basically like helium, for example, because of the planet going through a runaway gas effect that at the end, greenhouse effect at the end, that gassing basically resulted in the temperature becoming hotter and hotter, and the liquid water evaporated, and the water after that is actually split into hydrogen and helium, where for the most part the hydrogen was basically escaped the planet. Oxygen was remained on the planet, so the water split into oxygen and hydrogen. Hydrogen left because of the lighter materials. The oxygen combined with the carbon to form the main constituent now of the atmosphere in Venus, which is carbon dioxide. So this is in a nutshell, this unit. Okay. I hope that you guys are doing the reading actually on this materials, and answering all of the questions, and you have quizzes and things like that that are relevant to it. Okay. Okay, so let me introduce to you the next unit. So the next units are going to be units 37, 38, and then we're going to go into, I think, 39, 41, 45, and so on and so forth. So they're going to introduce to us some of these things up close. So we're going to start looking at the planets in the solar system. Obviously, we cannot do all of the planets. There is no way we can do all of the planets, because if we dedicate a whole unit just for per planet, those are 8 units already, okay? And then if we talk about their moons, I mean, even if we put them together, okay, talking about 16 units, that's the entire semester. So there is no way we can, then we will not do anything else. So there is no way we can do that. So this is what we're going to do instead. We're going to talk about the planets in general and how they're divided into 2 groups. We're going to talk about the Earth as a planet, because the Earth as a planet is actually serves as a very good starting point, because it's accessible, something that we can measure, something that we can observe. So it's actually going to serve as a good example for us, okay? Then as an example of moons, at least from the inner planets, and it's a terrible example, we're going to take our moon, the Earth's moon. Why it's a terrible example? because it's an odd thing. As a matter of fact, if you look at the inner planets, 2 of them have no moons whatsoever, Mercury and Venus. And one of them, Mars, has a moon, 2 moons, I'm sorry, and those 2 moons are rocky, small, tiny. They have nothing to do with the Earth's moon, and they are most likely captured asteroids. So the Earth's moon is an exception in terms of size, in terms of location, in terms of even how it formed, okay? And we're going to try to explain how the moon formed, because it's an odd thing. It's not a rule. So that is 2 critical things that we're going to talk about. And then as a sample from the solar system, I'm taking actually Venus. Venus has a lot of interesting things. We could have taken Mars, but Mars is all over the news. And honestly, it's not really that interesting. What is interesting about Venus is the fact that it is a twin planet sister to Earth. It's slightly less than Earth in terms of volume and in terms of mass. The composition is similar though. But something went completely wrong for one of them, namely Venus. So with that, and that is the challenge, would that happen to the Earth? Yes. Could that, I'm sorry, I should say, could that happen to the Earth? Yes. Will it happen to the Earth? It may be that we are already headed in that direction. That's really what this so we have to be careful, otherwise we might end up in that situation. So that's what is interesting about that planet. What is also interesting is in 2019, there was a publication about a material that was found in the atmosphere of Venus that indicates, or at least suggests, that maybe there is biology already going on the planet. Maybe there are living organisms on the planet. Because of the Russian, the Russian basically mission that it had a lander on Venus, we know Venus's surface temperature is so hot and the pressure is so high that it's not possible to even contemplate the idea that maybe there is life of the form that we know it, at least on its surface. Could it be in its atmosphere though? And that is something that we're trying to explore now. Granted, that study that was published in 2019 now has been basically, there were some flaws in it. And but the idea of life on Venus is not far-fetched. As a matter of fact, it's very possible that there is a life as we know it in its atmosphere. And because its atmosphere is not that really terrible in terms of temperature, in terms of pressure, there is a concentration of carbon dioxide though, and sulfuric acid, that's still a problem, but that's something else that is probably happening in that planet. Now, that stirred, of course, the interest of NASA and other groups trying to go and explore that planet. So this is something that we're going to look at. And the biggest really reason is because of the comparison between Earth and it, and the situation that that planet ended up with. As a matter of fact, about 150 million to about 400 or to 500 million years ago, those 2 planets, they were identical. In other words, Venus also had water on its surface. It had actually, it had all similar features to the Earth, slightly hotter than Earth, but other than that, it's identical to what the Earth is. That's going to be part of a problem that we're going to have in the homework assignment. Okay. Then we have also, then from the outer planets, we're going to take, of course, the 2 big players, namely Jupiter and Saturn. We're going to take them at once. Okay. We had missions to both of them, and the potential of life, actually, that's why they're also interesting, is in their moons, not in themselves, not on the 2 planets. Obviously, after that, we're going to turn our attention to the moons in the solar system, and then actually the dwarf planets and all of the other things in the solar system. I think we are going to cover a lot of materials in the solar system without covering everything, but we should be able to cover enough to have a full understanding of it. Once we go through everything in the solar system, including the comets and everything, we're going to turn our attention to the stars. And as you might have guessed right now, we always start with what is the most familiar. And let me ask you a question in here, and I want you guys to comment on it in here to tell me, what is the most familiar star that you guys can think of? that we should start with? Or should I say, which one is the easiest start to start with? That is star. Okay. You guys agree with Joseph? Yeah, that's the easiest one that we have access to. It's the closest one. So that's really what we're going to do. We're going to take the sun. And then we start moving upward in the scale and find a different model for all the stars and hopefully complete everything. Okay, so this is basically the entire unit, right? I don't think that we have enough time actually to introduce even 37, especially in light of the fact that you have a review for an exam that is coming, the midterm. You also have a project that you guys are starting on Tuesday of next week. I mean, this coming Tuesday. Today is what, Thursday, Friday, Saturday, Sunday, Monday, and then Tuesday. So you have your first observation on that day. So there is a lot of work that needs to be done. And I'm hoping that you guys focus on these things and start going with it. Sounds good? Okay, thank you. So I'm going to stop the recording unless you guys have any question or something is not clear. And I will see you guys in next week.